1, 2 minus v of 1, which is just v of 1, 2, because the v of 1 is canceled, plus v of 1, 2, 3 minus v of 1, 2 is just v of 1, 2, 3, because the v of 1, 2 is canceled. Right? So the sum across this row is v of n, or v of the worth of the grand coalition, 1, 2, 3. What about the second row? Well, if we add this to this, so v of 1 plus v of 1, 3 minus v of 1 is just v of 1, 3, because the v of 1 is canceled. If we add this to this, that's just v of 1, 2, 3, because the v of 1, 3 is canceled. So the sum across this row is also v of 1, 2, 3, or the worth of the grand coalition. Let's go to the third row. That we have, if we add v of 2 to v of 1, 2 minus v of 2, we get v of 1, 2. And if we add that to v of 1, 2, 3 minus v of 1, 2, we just get v of 1, 2, 3, the worth of the grand coalition. So across any row, the sum is the worth of the grand coalition. So if we then add this, add this, add this, add this, add this, in each of these 6 cases, we get v of n. And if we then take the average of 6 occurrences of v of n, of course it's v of n. So basically, the average of the sums is equal to the sum of the averages. That's essentially the proof of Pareto optimality. That in each case, when we take the average of all of those elements in the matrix, we will get v of n. So that is Pareto optimality. Again, stop me or unmic yourself and chime in if you have any questions. What about the null player axiom? That's pretty straightforward too, because again, going back to the generic 3-player game, just to demonstrate that this is the case, if each of these entries, so the null player axiom says that when player 1 joins player 2, the only benefit it generates, the only surplus it generates is the worth v of 1, the worth v of 1. That is, it doesn't generate anything extra beyond its own worth. So in effect, this is v of 1, this is v of 1, this is v of 1, because this is a null player, this is v of 1, because it's a null player, this is v of 1, this is v of 1. And if we take the average of six occurrences of v of 1, we get v of 1. So by construction, this will necessarily award to a null player simply its individual worth, because all of its marginal contributions are its individual worth. So that establishes the null player axiom. Actually, we don't have to go down. What about anonymity? Anonymity says that if 2 players are essentially identical in that every time they join a coalition, they generate the same surplus, then in effect, that means that, for example, let's suppose players 1 and 2 are substitutes. That means all of player 1's marginal contributions are exactly the same as player 2's marginal contributions. So for example, here, when player 1 joins the coalition 1, 3, when it joins with player 3, it's exactly the same as if 2 were to join 1, 3. So this is equal to this, and et cetera, that all of these marginal contributions would be exactly the same. They would occur at a different on a different line, but they are exactly the same as the marginal contribution by player 2 to that coalition. So if they have the same entries, even if they're in a different order, the averages are going to be the same. So clearly, the Shapley value will satisfy the anonymity axiom, that substitutes will be assigned the same reward. Okay. And then the only other point to note in terms of additivity, that is pretty straightforward too, because what we're doing here is summing. And so whether we sum these marginal contributions to the game B and separately sum the marginal contributions to the game W and add up these two averages, or if we take the average of the sums, the sort of component-wise sums, we'll get the same number. So given the additive structure, we're simply taking the average of these values, that is, we're summing them and dividing by the total, we're clearly going to get the same number. So that given the additive structure of this formula, that this will necessarily preserve this additivity. So indeed, the Shapley value satisfies additivity as well. Okay, it's a more complicated issue to establish that this is the only solution that satisfies these properties, and we're not going to go through that, but indeed, this is the main result that Shapley established. And so not only did he give us this sort of nice sort of closed form expression, this formula by which we can compute the Shapley value, but in addition, in order to sort of make a stronger argument in favor of this, he provided a list of axioms and established that this is the unique solution to satisfy those axioms. And this is called an axiomatic characterization. So this, by the way, we'll see other examples of axiomatic characterizations, but this is a very strong argument to sort of put down general principles that we think a solution in any context should satisfy, and then to not only demonstrate that it's possible to have all of these nice properties, but that these force us to use one specific solution is a very strong mathematical result. And it's very compelling because we can very often agree to general principles. And if those force us to agree overall to the outcome, that's rather compelling. Okay. So that is the Shapley value. And now I want to turn to another value called the nucleolus. And this is sort of a complicated definition and construction, but it's intuitive, it's reasonable. So I want you to stop me along the way if you have any questions. And we'll look at a couple examples at the end, but it's a little bit of an arduous process to get there. So I would also mention, by the way, that we saw in the left-hand, right-hand glove example that the Shapley value need not be in the core. So it might be unstable if we recommend that solution or that payoff vector for the group as a whole. It could very well be the case that some subgroup would be in a position to say that no, we'd rather split off and go our own way, because in fact the Shapley value need not be in the core. The nucleolus is always in the core when the core is non-empty. So this is sometimes referred to as a core selection. It picks out a point. Notice that the core is a whole set of points. Sometimes it's very large, but the nucleolus recommends a specific point in the core when the core is non-empty. And even when the core is empty, the nucleolus will continue to exist. So this is very nice in that sense, in that it's stable when the core is non-empty, and even when the core is empty, it still makes a specific recommendation. Okay, so the nucleolus is defined as follows, and again, there will be several steps in this, so I'm going to try to go slowly. Let's suppose we have two lists. We have a list of numbers. So arbitrary numbers. This is just to define notation: 7, -2, 1, 0, 7, 10, -3. This notation, theta of y, this is sort of an operator. It's going to operate on y, and all it's going to do is rearrange y in decreasing or non-increasing order. So it's going to start from the highest and work to the lowest. Okay, so you can see here that the highest of these numbers is 10. So this is going to be first in the ordered vector. Then the next highest are these two 7s. They'll appear here. It doesn't matter which order they appear in, but just that they both appear. Next, there's 10, 7, 7. The next highest is 1. That appears here. The next highest is 0. That occurs here. The next highest is -2. That occurs here. And the next highest is -3. So theta of y is going to reorder y in decreasing or non-increasing order, okay? So we'll refer to this as the ordered vector of y. Okay, next let me define what's called the lexicographic ordering. And before I define this, let me remind you of something. When you're looking up words in a dictionary, by the way, lexicographic, this is sometimes referred to as the dictionary ordering. Lexicography, lexico, the prefix, means words. So when you're looking up words in a dictionary, how do you do so? So you're looking up sort of, say, light and computer. But you know that computer will occur before light in the dictionary because you start off by looking at the first letter. And if the first letter of computer precedes the first letter of light, then it appears first, right? And what if you're looking at computer versus correspondence? Which comes first in the dictionary? Well, the way you go about determining that is you look at the first letter. They have the same first letter. So you go to the C section of the dictionary. Then computer versus correspondence, you go to the second letter. Yes, but they have the same second letter as well. So you go to the, hold on, let me see. I'm not sure this is going to work, but I'm going to try this. It might just disconnect me if I switch.